Participants, our second speaker have joined. Let me introduce the speaker to you. Our second speaker is Dr. Preeta.
Recording in progress.
It's our privilege to host an esteemed guest to this Atal Fdp. Let me introduce the speaker to you. She is a distinguished academician and researcher with over 16 years of teaching and research experience, currently serving as a research fellow at the Center for Business in Society, Coventry University, UK. She has an impressive portfolio of achievements. Dr. Preeta has received the Bharat Ratna Dr. Abdul Kalam Gold Medal for her contributions to her individual achievement and national development. She is a recognized supervisor at Anna University and SRM University, guiding the next generation of researchers. Her work has been published in several high profile journals, and she has also presented papers at international conferences, showcasing her expertise in the fields like medical image processing and artificial intelligence. We are truly privileged to have such an accomplished individual among us today. Let us welcome Preeta ma'am to this session and let us proceed with this event. Welcome you, ma'am.
Um, Hello, ma'am. Thank you for the great introduction, and thank you for all the participants who have joined here because I appreciate them because I know you are all towards the end of the week, and uh, and you are approaching. No, this is Friday evening, and I don't have. I have not seen people here around UK working in the evenings, and this is a great thing. People generally don't work in the evenings, and people don't work in Saturdays and Sundays and the weekends here. But we Indians, we work hard, and this is the thing which we have to really appreciate. And thank you for giving me this opportunity as well. First of all, let me introduce myself. You have said a lot, but myself, I would introduce myself like I'm Dr. Preeta. I have worked in various engineering colleges in India, as you all have is being working now. But and then I moved over to UK for the past 3 years, and I did my research um, in image processing, medical image processing. I did it by 2017, and then I worked in engineering colleges there. And I'm into here, but in UK, there are lots of teaching opportunities, but I preferred research, and I'm doing research here in a different environment. It's regarding cybersecurity, which you were speaking in the past lecture. I have to. I'm able to hear the last few seconds of the past lecture. So you are speaking about the cybersecurity, and there were lots and lots of opportunities here in UK. It's a key area, the cybersecurity and AI, and many universities are looking for such research environments or sort of researchers in this area. I hope everyone is able to hear me. Am I audible and visible? Could you please confirm that I'm audible? Yeah.
Yes,
Okay.
ma'am.
Thank
Yes,
you.
ma'am. You are audible, ma'am.
Yeah. So let me share my screen. Give me a few minutes so that I can share my screen. Yeah. So I hope you can view. So I'm going to take a lecture on this topic, which is AI enhanced robotics in surgery, improving precision and outcomes. So this topic is really much more closer to my heart because we people, when we do research, we work on this medical images and these things a lot, and then whenever we read those researches or thesis, it is much more interested, and we love to learn a lot in that area, being in a different area nowadays. when I take this research and look into this, it was a great experience for me. Because of this workshop or this lecture, I have this happened. And this in this lecture, I would like to say a few things about the robotics and its areas to develop, and then the an application where how do these robots do the surgery, and what kind of robots are available in this real time environment, and how do they perform those surgeries. And then finally a small hands-on session on Google Colab. And every people nowadays know they have all the programs in their hand, they have all the environments and everything. But we don't people we don't try to work on that, and we don't have time or ability to do after working hours. So that's the thing, we don't use many of the options which is available nowadays, because mm, writing a paper is a very difficult thing. But many of us don't know there is a app or there is a feature called overleaf, where we could do the writings of the paper in a very clear and final PDF manner. So it will be like a very clear aligned process, where we can write the paper clearly. So I used to write in Microsoft Word, so every time. But when we research more and more in this Google environment, we can get much more ideas about overleaf. And I encourage you to write papers in overleaf, so that it will be easy for you to for the alignment and process. It's like a LaTeX version. So here, while coming to this topic, AI enhanced robotics in surgery, improving precision and outcomes, let me introduce first what is AI. So here is the content what I'm going to speak for the next 1 hour or 1.5 hours. So first I have given what is the introduction, and what is an AI, and why AI is used in the surgery, and then how this robots evolved. So what is the in which year it evolved, and how it is now, and which place it is now. So those things I have given a few slides. And then I would introduce AI technologies. So many AI technologies more than this, but I'm particularly I'm speaking about ML, computer vision, which I have mentioned here as CV, and then the natural language processing. And then I've choose brain tumor surgery. Of course, I've done this brain tumor thesis. So surgery and the techniques based on the computer vision and ML. So in the PhD, so I have choose this brain tumor surgery as one of the application, how robots do this brain tumor surgery nowadays. And then few slides regarding the program or the sample code, which you can work with me in a hands-on session. And then the conclusion with my list of publications and references. So here we go. So the first slide is about the introduction. You all, or teachers, you are all lecturers, you might have introduced this AI to your students, so you all know what is AI. So but I will just say one line about AI is the machine with human intelligence. We say as one type, one field of AI. So there are many AIs, many AIs in the worldwide environment. But here in this session, I would speak about the machine with human intelligence. So when we speak about this robots, what comes into our mind? What comes into your mind when we speak about the term robot? Only one thing, we Tamil people or we Indian people comes to mind is the movie, whichever the robot. I hope you could get that movies pictures or movies remembrance. No, so how this robot works. So it can automatically learn from the data. It thinks. It can analyze the data, and it itself can perform the tasks. So it can do its work like a human. So that kind of AI is what I'm going to speak in this lecture. you know so this computer vision, this AI or this robot has three fields. So it needs three fields to work. So the biggest field, one among, is the computer vision. So the robot is nothing but uh, one, it is programmed with the field called computer vision. So what is computer vision? So computer vision, in the title it says viewing vision. So viewing the object, or viewing some kind of object in a body, or object in a place. So if we command the robot to go and take that object, so it has to go and take the object clearly by seeing, by having a good image, by having a good um, high definition images. It should properly pick that particular image, particular object. Okay, so that kind of programming is computer vision. How can it do that? So a robot is programmed with some data sets, predefined data sets. If I'm going to ask to the robot to go and pick that square shaped box, it has to be programmed with the square shaped box and its color and its features already, so that the robot goes and picks that particular box. So by seeing it, so that we say it as computer vision. And coming to the second field, which we say the machine learning. The machine learning is another field, is a different field. So this machine learning is needed to analyze the object. So whatever it has picked, it has to analyze. It has to compare it with its historical data, what it has been stored already, and processing, analyzing, reasoning. All this comes under this machine learning. And coming to the third biggest area, which is a hot topic nowadays, the deep learning. The deep learning is one of the area which is used to analyze with complex data patterns. We can also include the natural language processing under this deep learning. So this natural language processing involves programming the robot with languages so that it understands what the surgeon, what the commander speaks directly, without any programs or without any written text or anything. The robot understands what the commander says. So this is a very, very big process, I know, the natural language processing. So these all big fields are programmed into the robot to understand what is AI, to work on AI, to program on AI. So these comes under this robots. So moving on to the next slide. So what is AI? AI is reasoning, learning, solving the problem, and making a decision. So this field of AI based on robots, I've given this. So just it doesn't, any person, if I show if I show a banana and an apple, so they know the data sets before, because they have the memory. They know how the banana will look like, how the apple will look like. So whenever I give a banana, you can easily choose the banana rightly. But a third architecture or third instrument or a machine has to choose which is the banana means. You have to program something related to that banana, the features, the color, the structures, and everything, how it will look like. And these things you have to program it earlier, so that it can learn that, it can reason whether this is banana or not, and then it can make a decision to pick whether banana or apple. So this is what we say it as the human intelligence that comes under AI. So why do we use AI in the surgery? So AI improves visualization and localization. So why we say this? Because AI is used in surgery. It means it has to, the robot has to pick the object what the surgeon says. Sometimes there might be a tissue retraction the robot has to remove a tissue from the body. So in that case, if the robot doesn't have proper visualization, doesn't have proper camera, if doesn't have proper images or videos, then it cannot take the right decision to pick which tissue, or it doesn't know which tissue has to be picked. So it is much more necessary to improve the visualization and localization, which is abnormal from the human. The human also can visualize and localize. Even the surgeon can visualize and localize. Okay, so but the robot, which we are saying to visualize and localize, should be much more 10 times or 100 times better than the human, so that there will be improvement in selecting the right tissue, the healthy tissue or the dead tissue or the diseased tissue. It has to visualize it correctly and localize the particular tissue. So that comes under this section that says why we need robots or AI in surgery. And the other thing is that surgeons have the better experience. That's the other thing than the robot. Even though it has good visualization and localization, the surgeons will have um, good experience in understanding the tissues and everything. But the robot can assist the surgeon by giving a clear idea of how the tissue looks like, how it is before 6 months or something like that. The second case why we need robots or AI in surgery is that it makes a minimally invasive surgery. What do we mean by minimally invasive surgery? That is, the surgeons, if he or she wants to put a cut over the skin, even however he or she tries, he cannot make a surgery without any deep cuts, because the hands, whenever we move, we unknowingly may destroy a healthy tissue. So we may put a deeper cut to remove a tissue or something. So whenever we say the robot to do a surgery, so it will it will approximate the tissue size, how much depth it has to put the cut. It will calculate, and it can do a much better surgery than the surgeon. So based on the tissue size, it can minimize the skin cut. So that we say it as minimally invasive surgery. And also, it can provide decisions to the surgeons. So we don't have robots to make the decision by its own and make the surgery by its own, but it can make the decisions and give it to the surgeons to do the work, to proceed the work. So suppose if we want to do a three-dimensional reconstruction of any tissue, so the robot will make a three-dimensional view and give it to the surgeon and says this is the tissue size, and we can make a surgery from this side of the body, and we can put the cut this much of cut, and this kind of decisions can the robots can make and help the surgeon to make the surgery much more better than if he is doing it alone. So that's why we need AI in surgery to make a robot. And these are the key points, whatever I have spoke before. So we need robots to make a surgery, or to make the output much more precise and much more fast. And also, many complex surgeries can be done easily. Performing highly delicate and complex surgeries. The third point I have given as a key point is that when a surgeon, as a surgeon or as a human, there might be a vast data stored, because the patient might have taken one set of images 6 months before, and after 6 months he or she might be taking another set of data, or another set of MRI or CT images after 6 months. So this vast amount of data cannot be memorized or recognized by a surgeon automatically. He has to look into all the records, but the robot can keep this in mind, can memorize these. It has its memory to hold the data, patient's data 6 months before or 1 year before. It can collect all the data sets during surgery, during surgery as well. So it has, while during surgery, that might be real time robots. So while doing the surgery, the robots can recognize or memorize or can bring back its memory, the data which it has stored 1 year before about the same patient, about the same condition. So it can compare the data sets and it can say this kind of surgery or this kind of complexities is arising. So you have to improve this way of surgery. So that kind of suggestion a robot can give. And also, before entering the operation theater, the surgeon can have an idea about the surgery. So this robots helps this kind of work. And if there are any complications, and it can give some suggestions about errors, how to improve safety. And as it puts a minimal cut or minimal invasive surgery, the recovery time for the patient will also be lesser. So these are the advantages by using this robots. And if there is any doubts or anything you want to ask me, you can stop me then and there. And I don't want to just say something continuously. And if you have any questions, you can just ask me. And I don't see the chat window here. Is there any questions? Yeah, I don't see any questions till now. Okay, let me continue. Okay, so this is a slide just to say how the surgery evolved from 1980 till now. So from 1980, when we are all kids, no, I'm a 80s kid. So when we are all kids, there were free hand surgery, there were no robots. And by the year 90 to 2000, we had some minimally invasive surgeries using robots. And now there are robot assisted surgery. So now we have robot assisted surgery. The surgeons use robots to do the surgery. I don't know how many of people in this link share or seeing this lecture have seen this robot assisted surgery. So there were many surgeries going on with robots. The robots will be there, and the surgeon will be using the robot to make the surgery. I'll show you a small video, which is 1 minute or less than that, which says how the robot stays there and how he does the surgery. And we are towards working towards a micro robotics, and there were people working on this area. This is also a biggest area where people can do research about micro robotics, that is the robots of 1 millimeter thickness. And people working on this or have great future, I think. So here, first level of the robot is like assistive autonomy. So this robot can make virtual fixtures and uh, can guide some guides can guidelines can be provided to this robots to make the surgery. So what I mean is this: if the surgeon says the surgeon will be insisted by the robot that if the surgeon is doing a surgery, he will get some instructions from this robot that you are entering inside this sensitive area, please don't go there. And the surgeon's hand movements are watched by these robots to maintain precision and safety. So this kind of actions this robots did in the level 1 robotic development. So level 2, so here, you know, the robots can understand the texture of the tissue when they are doing the sutures and all while doing the surgery. So this robots will give instructions about the sensitive areas or how the tissue thickness is, how you can make the sutures, and these kind of instructions this robots can give. And it also maintains the, it will monitor the surgeon's eyesight, whether his eyesight is concentrated on that particular tissue or not. This kind of if there is any deviations in that, this robot gives in some instructions. The second kind of level 2 is task execution. So task is execution is that the robots are given few instructions to do some part of the surgery. So I don't say it's a surgery, it's like a suturing, like stitches. So the robots automatically did the sutures by itself. I would like to show a small video here. So this kind of sutures the robot handles, do it by itself. So this instruction, if it is given by the surgeon, then the robots do such kind of sutures. This comes under the level 2 autonomy. And level 3 robots, it automatically performed certain segments of surgery like tissue extraction. So the level 2 is like suturing, and level 3 is tissue dissection. So some kind of tissue will be retracted from a part of the body, and this semi-autonomous surgery kind of robot. So here I have another sample animation video, which is, bear with me with any advertisements if it comes over. So this kind of surgery that is semi-autonomous, so the person or the surgeon will be sitting 1 meter away from the body or the patient, and he can control the arms of the of the robot to make the surgery. So this kind of semi-autonomous, or the robot can perform its own tissue dissection as well. The same thing, both comes into level 3. And then level 4 is adaptive autonomy, which says the robots will give feedback because it works in the real time surgery, and it can understand the data because it has its own historical data being stored in it. So it can understand the data clearly, and it can say if there is any complications because it knows the previous prior data. So if there is any complications now during surgery, it can insist the surgeon that you're going to get a complication there because there is some other tissue over this tissue. You cannot make this kind of actions. So this kind of instructions this robots give the surgeons during the surgery. That we say it as adaptive autonomy. And while we are coming to level 5, that's full autonomy, this level has not been reached, and we researchers are there to work towards this full autonomic robots, which can perform its own surgery, its own decision. It can remove the tissue or everything. But I would say The full autonomy is not required because there should be a human, because whenever we program a mission, that's a mission. So a full autonomy is not completely required. We need a surgeon, however, to just oversee the full autonomic procedures at least. So a surgeon has to approve everything, whatever the robots does. So that should be the full autonomic stage. So we need a human there. We cannot replace um, um, a robot instead of a surgeon at any time, anywhere. So this level 5 is under consideration, and it has not been fully developed. So this is what we have discussed already. So the machine learning, computer vision, and natural language processing, or three techniques, comes under this robots. So the artificial intelligence, we say the machine learning, to understand, to analyze the data, to view the data, we use computer vision. And then the third, natural language processing, is the one which the robot can get the data, get the information via speech. I know persons people doing thesis under this natural language processing, which is much more difficult at that stage, because when I was doing my PhD from 2012, I had my colleagues doing research under this area, and I found them difficult because they don't know how to get the data, where to start and where to end. There were people doing natural language processing thesis, PhD. So um, that is a sorry, main problem those days. But not now. I think there are so many helping Google links, and so many advanced apps are being developed in this area. So which helps nowadays people who are doing research in this area. So these three are the important thing which we need under this robots. So machine learning, coming into this machine learning. So I did my PhD in this machine learning and image processing. So where we need this machine learning? We need this machine learning before, during surgery, and after surgery, everywhere. Because pre-surgery means, once we get the data, once we get the patient into the hospital, if we to identify the patient, so whether he has tumor or not, we need to use some modality to identify the tumor inside the patient. If he has, or if he or she has a tumor, we need some modality to identify it. So once we identified the tumor, we need these tumors to be fed into the machine learning algorithm to get a clear analysis of where the tumor is, how, what was the boundary of the tumor, how it looks like, and what is the shape of the tumor, what is the shape of the brain, or if it is a brain tumor, whether it has been deformed. This kind of analysis should be done before entering into the next step. So pre-surgery, before the surgery, the analysis is completely done by this machine learning processor. And then during the surgery, if we use a real-time robot, real-time machine there, then it could predict the complications, how the data was looking before, how it is looking now. And this kind of comparisons this machine learning can make. It can analyze the data and it can give some output based on that. And after the surgery, it can record all the works what it has done before. So whether during the surgery, what are the complications, before the surgery, how it looked like. And this kind of data can be stored, and it can be followed up for the next surgery or for the next procedures. So machine learning is much more important in this day-to-day life, other than all the areas, I say. And then the next slide says the computer vision. This also comes under the three areas: before, between, and after. So here, the applications of this computer vision is viewing the object three dimensionally. So we need proper visualization cameras, good videos recorded, and real-time 3D imaging is necessary. So this kind of works comes under the computer vision. And we need also, I have already said, we need this vision much more good, because it the machine has to differentiate the healthy and diseased tissue. And then the augmented reality, which is virtual reality, like visualizing the image in a much more better three-dimensional version or in different angles. These things comes under this computer vision. And the natural language processing, the surgeons, if he gives some instructions to the robots has to get the instructions. And you should note that the surgeon is giving the instruction in voice. So he's just giving the voice instructions. The robot has to understand this voice commands, and it has to uh, make it into a text. It has to document it, and these kind of works comes under this natural language processing in surgical robots. So these are all the basics of robots, or basics of surgery, or basics of AI in surgery. So now coming into the topic called robots and brain tumor surgery. So as I have done brain tumor surgery, I have some analyzed some brain tumor surgery by robots. So the picture you're seeing on the right is or the different types of tumor. The different types of tumor can be, I have given the names nearby. So looking at the pictures, these are all the MRI images. Looking at the pictures, you can see the first image, this the first top row. You can see the first, second, and third image, and these are all the same patient's image. First image is taken from the top. We say it as an axial tumor. This, you can see the top of the head. So this is axial slice. And when you see the second image, we say it as the coronal view. That is the back side of the head. And this is a sagittal view. We see it from the sidewise. So all these three pieces of tumor are all from the same person. Top view looks like a circle. The back view looks like a different boundary. And the third sagittal view looks like a different boundary. So all these reconstruction or making all these interactions together is very much more difficult for the surgeon or any experienced sorry for any experienced person to analyze the boundary of the tumor. So this is what we say, the the irregular boundary. So here you, so even if it is looking like a circle, this is not a circle. And this is completely a brain. Brain is a semi solid like structure, and the tissue is much more jelly like type, and we cannot simply put in tools and instruments to cut over this tumor. So it's very difficult to see, understand what is the boundary of the tumor. And three-dimensional reconstruction by the robot is much more necessary in this brain tumor surgery, and to pre-plan. See, everywhere you can see different. This glioma looks different. This pituitary looks different, and everywhere the tumor looks, the boundary looks different. So it's much more necessary to use robots in brain tumor surgery. Coming to the next slide. So how do these robots perform brain tumor surgery? So first, the the robots are insisted to integrate the modalities, outputs of the modalities, like modality, I mean like MRI or CT imaging. So generally, brain tumor patients is n- uh, is allotted to take MRI images. So they have MRI images and CT images of a patient. And one time, if a patient is taking an MRI image, there will be 64 cross 64 cross 64 images. I mean, um, 64 slices in axial wise, that is top wise, 64 slices of MRI images from sagittal view, 64 slices in coronal view. So all sites will have 64 slices of images. So you think the brain, the head is sliced into 64 slices. So the image looks like that. Actually, we don't slice the head, but the sliced images of MRI is being taken. So there are lots and lots of data being taken from the MRI machine when we go for one MRI sitting. So like this, they take every 3 months or 6 months, they repeat this kind of MRIs. So this kind of imaging is all integrated together, and then it creates a three-dimensional model easily, not like a surgeon. Surgeons, it is very difficult for them to make this surgery, to make this three-dimensional view, but this robot easily makes a three-dimensional view. And then the second case is precise surgical assistance. Give me a minute. It's getting on cold here in UK. I'm sorry. Thank you. So, precise surgical assistance is that the um, whenever we use the tool, we cannot make a maneuver like maneuver means I say a movement like how the robot does.
Ma'am, excuse me, ma'am.
Yeah.
Ma'am, your slides are not moving, ma'am. It is in the second slide itself.
Oh, is it so?
Yes, ma'am. So we have the participants have intimated through chat. So I thought you might have seen that.
Mm-hmm. No, I'm just keeping it projected. So, is this? Can you view this now?
No, ma'am, it's not in the slideshow.
But I'm viewing. Stop sharing. I'm just sharing. No, I don't know why it is like that. So just I'll stop sharing, and then once again I will do the,
Okay, ma'am.
yeah. Is it now viewable?
Yeah, it's viewable, ma'am, but it's not in slideshow. Yeah, ma'am, it's changing now.
Can you now view this?
Yes, ma'am.
Oh, sorry. You could have said me this before. I'm sorry. So so people, you have not watched this video even. I've played some videos as well. So just I will show that once again. So this is the level one. So this is the level one. I hope you can view this now.
Yes, ma'am, yes.
Yeah, so this is a level one robotic surgery, and the next version of robotic surgery is should be this. Again, the video advertisement comes in.
Ma'am, video is not playing now.
Okay, so let me stop this. So I'll give you this link then so that you can view it later. Okay, I don't know what's the problem. Now, can you view my screen?
Your screen presently is at evolution of surgical robotics, ma'am.
Is that okay?
Yes, ma'am, it's moving now, but it is not in slideshow.
Yeah, if I put a slideshow, then you say that it's not, you cannot view the next slide, it gets freezed. So let me try
Okay,
again. I'll just put it in slideshow. If not,
I'll let you know, ma'am.
yeah. Can you view this now?
Still, it is not in slideshow, ma'am. Your
Oh,
contents are viewable in the left side also, and whichever content you have, whichever slide you have selected is been displayed on the right.
okay. Then it's moving, right?
Yeah, ma'am, it's moving.
Okay, then. So I don't know why it's not moving when I put it in slideshow. I don't know. But let me keep this. Can you see is this in slideshow last time? One last time.
Yeah, ma'am, I'll see and let you know.
Okay, is this visible? I'm just displaying the slide continued, CONTD,
Yes,
continued
yes,
slide.
yes. Visible.
You are okay.
Yeah,
Yeah,
level
thank
4 and level 5 are seen here.
you. Yeah, okay. Sorry, people. I don't know. I didn't know. I'm just. I was talking with the um, um, a projected slideshow, so I didn't know the chat and things. Whatever you are doing, so please tell me if you want anything. Stop me then and there, so that I can keep me updated. I can just move whatever I can do. I can help you. So, so this is what I'm speaking: machine learning, computer vision, and natural language processing. And yeah, so when we say about machine learning, so this machine learning is much more necessary before the surgery, during the surgery, and after surgery. I was speaking about this. So before the surgery, we needed to analyze the data. During the surgery, we need to say some, if there is any complications, this machine learning is necessary to intimate the surgeon that this complication comes in, so you have to stop making the surgery, or you have to make the surgery in this kind of process, or like that. So this machine learning helps the surgeon during the surgery as well. And after the surgery, it keeps a record of whatever the surgery, how the surgery was made, and that kind of um, um, things this machine learning does, this robots does in the post surgery. And coming to the computer vision, I hope you people can view my slides. I am displaying the computer vision in surgical robots. And here, the robots can make a three-dimensional imaging during surgery. So this is a much more big development in the surgical environment, because for making a three-dimensional imaging, because my project was a three-dimensional imaging, so for making a three-dimensional imaging, I did each and every process individually and then integrating all to make a three-dimensional view. But now the speed of the robot is being increased, so when it sees the image, it can, in a second, it can render the three-dimensional view of that image, which comes under this computer vision. So the speed, memory, and everything has been increased, which makes it easy to make a three-dimensional image in minutes during the surgery. So this is the biggest advancement that now we have. And this computer vision cameras can recognize the tissue, how healthy it is or how diseased it is, which part of this has to be removed and how it should be removed, and these kind of vision status can be provided by these robots. And the augmented reality is the virtual reality. you know it shows the image in a very different way. You might have used the VR cameras, um, playing cameras, just for an example I'm saying that. So this kind of cameras is much more um, very much advanced to make the vision clear. So the natural language processing is the next one. you know when we go into the natural language processing, this is a very 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 bigger area. I have said already, people working on this natural language processing does not know where to start and where to end. It's a very because it's a very very broad area. And making a speech to text and text to speech is nowadays we have much more and more apps doing this. But when I did my PhD, it was very difficult to do PhDs in this kind of area. So natural language processing is that the robot is getting the ability to understand what the surgeon speaks and make it into a text, document it. This kind of natural language processing is should be programmed in the robot. And here, this is what I was speaking about: robots in brain tumor surgery. You know, the images, whatever I have shown in the right, is the tumor. The first row of images is the first image is this three is one person's image. The first row of images. This is the top view of the image. We say it as axial. The second image we say it as coronal images, and this we say it as sagittal, the sidewise imaging. All these three are same tumors. So you can see the shape difference. The axial tumor has a different shape, this has a different shape, and this has a different shape. So it's very difficult to localize the tumor. It's very difficult to find a boundary of the tumor. It's difficult for an surgeon to identify where to put on the tool and where to maneuver and where to how to remove this kind of decisions. If there is some help for a surgeon, it be much more better to make the surgery a successful one. So
Ma'am,
this
excuse me,
of
ma'am. That image which you
yes,
are talking about is not visible, ma'am.
again, so I will just display it like this. Is this visible now?
Yes, ma'am. Yes.
Yeah, okay. So I'm speaking about this image. Okay, just okay. So I'm just speaking about this image, the meningioma image. This one is a top view, axial images. This is the back side or front side view. We say it as coronal, and this one is a sagittal image, which we say it as the sidewise image of an MRI. So all these three images, you can see the tumor shape is different. This is round one, this is some different structure, and this is some different structure. And once you see that, we cannot say that this is the boundary of the tumor. The tumor might be in this color here, but the surrounding tissue might be also a tumor. We cannot say this is not a tumor. So only the experienced surgeon and only the experienced one who is doing surgery regularly can understand which one will be the tumor or which not. So if this experience is fed into the robots, this will be a very big achievement, and that is what happening nowadays. So how do this robots perform the surgery? It takes the MRI data, it takes the CT data. Specifically, we say only MRI data is used for this tumor prediction, because MRI differentiates soft tissue and hard tissues. CT does not. Computer tomography modality does not differentiate hard and soft tissues. You know, what I'm speaking is MRI is suitable for brain because brain has soft tissues, many soft tissues. The structure, the how it will look like. But CT is specifically designed for hard tissues. that is like bones or something. So MRI is specifically used for this brain tumor. So this brain tumor images, that 64 cross 64 cross 64 images taken from this MRI is used to get the 3D-dimensional model. So this three-dimensional model, no surgeon can make a three-dimensional model himself. So he needs an assistant to make it. The assistant, we say it as a robot. And then, robots can perform the surgery with no hand tremors. So most of the surgeons does not have hand tremors, but in some cases, if they have some hand tremors, because they are also humans, when they are doing a brain surgery, they might have some problems to make some um, maneuvers or movements in the brain. So this robot handle can make a high stable is a high stable machine to clearly cut out the tissue, and also the minimally invasive one. And this is a real time this robot makes a real time guidance and monitoring to the surgeon. So the surgeon can understand, based on the robot's decision, and he can make the surgery in a much more better way than himself doing the surgery. So so I can say some examples of some robots. You might have known this, but we say a robot giving assistance to the surgeon, we call it as Rosa robot. And then the robot doing brain tumor surgeries, we call it as neuro arm. And the robot which is used in spine surgeries, we say it as Maser robots. So these are all the pros, that is minimally invasive, reduced risks, and everything. But the cons is that the surgeons is the one who is the main actor, and this robots are the second actors, which can help the surgeons. And completely we cannot depend on the robots to make a surgery. And here comes an image showing a brain. So this is an animated image, not the original image. So you can see the brain on the left side, a small box on the left. This small box is the brain, complete brain. And I have just zoomed up a small part of this brain. You can see a small box there. Inside the box, a small box again. That box is being enlarged here. So that part is this one. See how minute it is. And here is a cell called oligodendrocyte, and here is a cell called astrocyte. This is like a medical session actually, but I wanted to say that if there is a tumor here, then we say it as oligodendrocytoma. And if there is a tumor here in the green colored cell, we say it as astrocytoma. See how minute it is. And if we want to remove a tissue here in this place, see it's very minute. And just have enlarged this one. So it's a very minute one. And if the tumor size is 2 millimeter or below one centimeter, might be. So it is not easy for a surgeon or for a human hands to remove this part. So we definitely need robots to do this. So the difficulties the surgeons face is that the brain cells might take a different shape because of the tumor, because the tumor is big and it is going and putting pressure on the adjacent cells, so it might be looking like a different shape. Brain is looking like a different shape. The tumor and edema tissues has to be removed. The ambiguity in the structural boundaries, three-dimensional reconstruction, the computational time, and everything is difficult, whatever I have mentioned before. So these are all the difficulties in the tumor surgery, and we need um, a particular specific robot to remove this tissue, brain tumor tissue. So here comes the block diagram, what which speaks about this surgery. So you might have many of you might have done this PhD, or might be doing this PhD in medical images, and you have to get a real time, or you have to get an image, a real image from the scan centers, and then you have to do the procedures, you have to do the pre-processing, segmentation, or feature extraction, whatever you have to do with that. So when I was doing my PhD, I didn't have any sources from the internet, but nowadays we have too many sources in the internet, and another app to say where the source is, which source to use, and these kinds of instructions are there in the Google now. But those days, I we went to the centers, scan centers, to collect this kind of MRI images. The first and the foremost thing to start image processing in medical image processing is that you need a real MRI image, which is called a DICOM image. DICOM is digital communication image. You cannot do a medical image processing project or thesis using JPEG, using PNG. You cannot use an PNG image to do the work. You need an image called, with the extension called .dcm. We need an image called um, image1.dcm, DICOM. So DICOM is the full extension. Um, Shortly, it will be displayed like .dcm. So unless that, you cannot do this image processing, medical image processing. So this is available in so many data sources in the internet. And for sample, you can use any JPEG or PNG image. But when you're doing a PhD, when you're doing a thesis work, you definitely need a DICOM image. And this DICOM image is then pre-processed. So pre-processing is that MRI image may add some noises, because MRI machine is not a noiseless machine, it is a noisiest machine. So it will include some pixels, uh, noise pixels in the image. So that has to be removed first. And then you have to segment the tumor from the head, that means from the image that is displaying only the tumor. So display only the tumor using segmentation. And then you have to extract the features, and then classify, then optimize, and then three-dimensional reconstruct. So these are the works. The machine is doing it automatically in seconds or fractions of a minute to render a three-dimensional image. But when you want to work on this, you have to work on each and every block to understand what it is. So here in this end of the session, I think I should finish it in another half an hour. So I'll just rush up with these slides, and I will give a sample program to be done in the Colab, Google Colab, to segment a tumor from the image. Yeah. So, okay. So pre-processing is that removing noise. So generally, for an MRI image, we use Russian filtering. So Russian filtering is suitable for MRI images. There is a paper also mentioning this. So I used Russian filtering to remove MRI images noise. So initially I checked it with median filtering, because at those days I know only median filtering or region growing, that kind of basic pre-processing techniques. And then finally I came to know that Russian filtering is the best filter to remove noise from this MRI image. So just I used this. So you might have different papers on this read out after the period of 2017. So you can just look into which is the best filter to remove this MRI. So what is this Russian filter? Russian noise means the MRI image will include bias. That means a value, a common value to the entire pixels in the image. Like a 3 will be added to all the pixel values. Consider the pixel value is 125, 121, and it is like that. So this MRI image will be subjected to add 3, number 3 or 4 or 5, some value will be added commonly throughout the picture, throughout the MRI. That's the disadvantage in MRI. So you use Russian filtering to minimize that bias. So if there is even low SNR, low signal to noise ratio, and the complete picture, then it is very difficult using Russian filtering, because Russian filtering will render no output. So there should be no low SNR. The SNR should be high, as well as can, if it is high, you can use Russian filtering. So that is the process in pre-processing. And you can also use Gaussian filtering. Gaussian filtering also works well to remove the white noise. And after pre-processing, this is the output you can get. So the first picture shows the original image. Second picture, I what the is the result what I got after median filtering. So this is like much more funny to look, because the shape of the tumor, the shape of the brain itself is different. You can see the median filtering, because median filtering just averages the neighboring pixels and place it in the current pixel. So see, it's brighter. You can see the image looks brighter, but the shape is completely different. So then I used Russian filtering. You can compare the original and the Russian filtering. It was much more similar, better. The noise is being reduced. So this is the output. So I use Russian filtering to do this pre-processing. And there are so many segmentation methods. I have listed out 4 to 6 segmentation methods. Um, People doing work in this area will definitely know what is region growing, fuzzy C means, K means, and everything. So I don't want to go into every each and every technique, but I'm today going to show a hands-on session on this fuzzy C means clustering, because that clustering, what I did it in PhD, so I just use this. But there are so many advanced techniques nowadays. So you can use graph, snake algorithms, active contours. You can use conventional neural networks, and so many algorithms are there to make the segmentation. So conventional neural network is the current technique. I think so many papers, they are using the segmentation method to, because this is a deep learning based method. It can learn, train, and label data and identify features. So I think convolutional neural networks is the current hot topic. And after doing this segmentation, um, you can see the um, color of the tumor is brighter. The other parts of the brain is not much more brighter. So you can say that the intensity level of the tumor is high. So on that basis, you will get the skull also at the output. See, you can see the skull also at the output. Because this is a tumor, I will also get the same kind of intensity as output. So you have to use some erosion technique to remove that skull area. And I did, it was so many, we have to do the program ourselves. But nowadays there are so much programs available in the Google, the GitHub areas. Many people use GitHub, and lot of programs is being downloaded in that GitHubs, so that they work in environment collaboratively. So you can use many of the techniques. And after segmentation, that I have shown the axial value, the axial image, and it looks like this. The sagittal image looks like this, and coronal image after segmentation looks like this. But you can see it is not same. There is some difference. So based on the images, now I have used FCM. So that is the fuzzy C means algorithm. So it looks a different output. You can use so many segmentation techniques like CNN or anything and make the view better. And here comes a feature extraction. So feature extraction is that after segmentation, I should confirm whether the area I have segmented is a tumor. So what I do is I take the feature of the tumor, I take the feature of a non-tumor area, then I feed both into the machine, so that the machine learns the tumor features and the non-tumor features. Now, when I go and show a tumor picture, based on the learning, it will say whether this is tumor or not. So that I need some features of tumor and non-tumor. So what I do before starting a program, I will train the robot with a tumored cell. That is, this kind of feature says this is tumor. This, if the mean comes 10 or 9, then it's a tumor. If the median comes this much, then it's a tumor. So like that features I have to train the machine. And also I will train some features which is non-tumor as well. Then I will show the robot whether this is tumor or not, any image, then it can perfectly classify, yes, this is a tumor, this is not a tumor. This is the similar case like apple and banana. Apple and bananas feature is set to the robot in prior, and when I show the banana, it can automatically say yes, this is banana because it is yellow in color, this is long, and these kind of inputs it has been trained. So based on that, it can rightly choose the banana. So I need a feature extraction techniques. These are the sample features, and here there are 36 number of features I have mentioned: mean, variance, standard deviation, median, skewness, kurtosis, gray level co-occurrence matrix, contrast, correlation. So there are so many features like this, and these are the values for the feature, sample values. So if the value exceeds a particular value, we say that as a tumor and not. So then we can use support vector mission. I think this is one of the good, one of the best method to classify tumor and a non-tumor. So imagine the square boxes are non-tumored features. The circle boxes are tumored features. This robot can classify whether it's a tumor or not. So if it is a tumor, only you will get circles. So it says only tumor features are there. If it is a non-tumor, you will get only the squares. You will not get the circles. So I can say, so classify and say whether it is tumor or not. So in a simple version, I have said it, but these are the um, support vectors. So the one which is near to this line, this dotted line, the vectors which is nearer to this dotted lines is say it's said to be support vectors. So using these support vectors, the machine will construct a hyperplane like this. So this hyperplane is made in such a way, it divides it, the both non-tumor and tumor pixels in a proper way. So it should be properly fixed. So that is the work of the support vector. And then it can, whatever image you give, it can classify like this and then find whether it is tumor or not. So I have said it in a simple way. There are so many formulas and parameters which we have to think about while we see this in the support vector mission. And there are too many videos and too many um, uh, calculations which you can view um, in Google pages nowadays and learn the support vector mission. Then actually we do, after this we do optimization. So optimization is should be done because to make it much more efficient, this is medical image and this is not some other image. So it is very essential to make the output 100% accurate, so not lesser than, because this is human life. So we have to make it 100% accurate. We use optimization. So we have to tune some of the parameters which we use in the support vector mission. So in support vector mission, we use a formula which has two parameters called C and gamma. So whenever you do the work, you might have you might understand. So this will have too many parameters in the formula, and some parameter will be contradictory. If we increase one value, the other value goes down. If we decrease that value, other values goes up. So that contradictory value should be kept correctly to get the output perfectly. That comes under optimization. So we should get the correct output for whatever input we give. So we have to adjust the parameters in that way. And then comes the three-dimensional reconstruction. So the robots use the fast shear warp volume rendering method. That is, um, you take axial slices, 64 slices of axial images, segment the tumor for all the 64 slices, and then overlap all the tumor pixels alone, one above the other, to make a three-dimensional view. So I have just shown a replication of this, but I don't know how much you can understand. But Um, Consider the first slice of the head has this kind of structure. I have just segmented. The second tumor slice is like this. The third tumor slice is like this. Now overlap everything one above the other. Stack it. So like this, we do it for axial, coronal, and sagittal. Integrate all these three sets. You get a three-dimensional view. So this is how the three-dimensional view of the head of the brain tumor is taken out. This takes a lot of time. It's not easy to just say, because when we run the code, it will run for 6 to 7 hours those days, because it has to take the features, it has to calculate, then it has to take these tumor slices, all axial, coronal, and all three sides. It has to integrate. And sometimes I just run the program and then go for sleep in the night, and in the morning there will be some output. So this happens, those days. So this kind of but nowadays it has made very very fast, so it renders a three-dimensional image in a quick way. So this is the axial, coronal, sagittal view. This is how it looks like. This is the picture I got from the Google, um, like book. When you just see the book, there are so many papers in the book, and when we see it in another angle, it will be in a different shape. So make that like that. This axial slices, coronal, sagittal slices are kept one above the other. So this is how. So in any side we have to view, not only in one direction. In all three-dimensional view means we should rotate the image. In any view, it has to show the proper boundary. So that's the challenge we have in this three-dimensional view. And this is what I want to say. And here comes the uh, yeah, here comes the programming part. We have 14 more minutes, but I would say, if you can, I know you are all at 8:50 or 8:50 p.m. at that timing, so I can understand, but I will just show this, and you can work out tomorrow or any time. I'll just give a quick note on this. So first, you download, if you can, you can do this now. Download any brain tumor image, any grayscale or color image. So I have just chosen grayscale image in JPEG format, because for DICOM images you have to go to a particular website. Even though I have the website, and it's not necessary for me to now to download that. It's a big file. People who needs that can go and search in the Google. That is available openly, in open access. Everyone can go and download. So here I've just chosen the JPEG image. So in the Google, brain tumor image grayscale, that's what I have typed. So when you type, I hope you can view my screen. If not, please tell me.
It's viewable, ma'am. It's viewable.
Yeah, thank you. I'm just typing. So any images you can download. I've chosen this image. You just place this in anywhere in your system. Okay. And then I have chosen to take the Google Colab. So just go to Google Colab. And the thing in Google Colab is that you cannot directly place the pictures path in the program. You can use any Python environment or MATLAB environment. I usually use Python environment, but for you, I thought I would finish by 3 o'clock, and then I can, sorry, for me it's 3, for you by 8 o'clock, and then for half an hour I can show you this code. But as it is a short time period, I'm just showing it in Google Colab. You can also use Python library or idle platform to run this code. So when you go into this screen displays, and you all know this, I know you all might have thought for your students. So just pick a new notebook, and then here you start coding, show your codes, and you type your code whatever you need here, and then just give run. Here you can see the output. So for this code, I don't know whether I can finish, but I'll just try copying and pasting here. And if you have time also, just work on this. So I need to install few installations to make this code run, because this is the FCM or fuzzy C means based segmentation. So I need few installations to be done to work on the fuzzy C means as well as the images. So I just install pip install scikit is the library which can import all the images. And again, I do pip install. Pip install is a Python environment installation, and I can use the scikit to download the fuzzy based images, and then I click run. So when I run this, it will automatically install these functions so that you can work on your code. So now it has finished running. So I just add on another cell to start working on this. So I need few libraries to be installed. So I just install those things. All the files just from Google Colab. Also, I need to import NumPy. NumPy is a numerical calculation done by Python. So import NumPy as, let me put it as NP. So everywhere we use this kind of libraries to be installed. So wherever I want to put NumPy, I use NP. And then,
Ma'am, excuse me, ma'am. The program screen is not
yes,
visible now.
uh, I don't know actually what to do now. Okay, so let me show you on the PowerPoint itself. I'll just stop sharing and then do it once again. Let me try. Mm, Is it visible now?
Yes, ma'am. Yes.
Yes, okay. So first I just installed these two functions using Python. Pip install scikit image to make all the images to view. Pip install scikit fuzzy to use this fuzzy c-means algorithm, and just it worked, and it gave me to continue. Now I'm doing some libraries, installing, including some libraries to work on my code. So this libraries matplotlib dot pyplot as plt, it is showing me. Yeah. So I have imported 3 of them, and also I need sk image .io, and I want to import imread, and then I also need to import skfussy as first. I need to import from skimage and import all the filters. So these six libraries I have installed, because one is for Colab to import all the files. The second one is numpy as np, that is a number calculations. We have to calculations to be done in this Python environment. Matplotlib is to plot any uh, outputs, the graphs or something. And then the next thing is to import the um, imread function. Imread function reads all the pixels into a file, and then we are using fuzzy cmeans environment. So the fuzzy cmeans is to just make the fuzzy output. And then the last one is to use a Gaussian filter. I'm using Gaussian filter here because I have just downloaded the JPEG image. So we are using only the filters. I'm going to use one of the filters. So just I press play here, and it says yes, I've taken these libraries. So it just shows a tick mark here, and then again I put a code, and I thought of typing this, but I don't have time. So let's see where I have this. You can get many codes like this, and use it here. So I'll say what it is. The first one is the uploaded files dot upload of. So this line, what it does is it uploads, because this Google Colab, we cannot give the direct file path here, because in MATLAB or Python, if you have used that, you can place the path, the file path there, but here we cannot do that. So it has to take the image, the Google Colab has to pick the image from some location. So this instruction will take the image and put it in a dictionary as a key. Your image will be placed as a key in this dictionary, and then we load this image into the image file name. So the first image, you can upload many files using this command. You can upload 4 to 5 files or anything. So here we are going to upload only one. So the next line, when you say your uploaded images will be stored in this file name, that is, your image is stored in this image file name. And then the next one, we read the image file name, image file, that is, we take all the pixel values and put it in a file name called image. So this is converted to grayscale and then put it into image. So you can even download color image too for this code. And then I pre-process the image using Gaussian filter. So in this Python environment, we don't need to specify the formula or anything. Directly give it as Gaussian. And I have mentioned sigma here. The sigma is nothing but, you should recognize the formula for Gaussian. Gaussian has the sigma character, sigma parameter. I could show that in this function. If you could see me, if you could see this, I don't know whether this is sharing or not. The Gaussian formula, it's Gaussian. So here you can see this formula. It has a sigma parameter. Sigma is a standard deviation. All others are the simple constraints. No, it's not. It's a constant. E is the Euler's number. X and Y are the coordinates of the pixel. Sigma is alone variable. Sigma is the standard deviation. So that sigma value, we mention it here as 1, because more than this will make the image much more blurred. It is just smoothening image, so it's enough if you give 1. And then we flatten the image. Image flattening is done because we are going to do fuzzy C means. Fuzzy C means does not work on the matrix. It works on one dimensional image. You know, it will convert it to a one dimensional view. And then fuzzy C means needs the number of clusters to be specified. So how many clusters the image should have. And then this is the syntax for the fuzzy C means. So I'll say what is fuzzy C means. Each and every pixel in the image, if you think that the image has three clusters in the sense is that intensity, if there are three intensities in an image, like one dark, one gray, one white, so three different intensities, color intensities in an image, then fuzzy C means what it will do is each pixel will be said which cluster it belongs using the membership function. Each cluster will have three values like zero point 0.2, zero point 0.7, and zero point 0.3. So zero point 0.2 means it is a membership value for the first cluster. So first cluster is very less, zero point 0.2 is very less. Second cluster, it says that it has zero point 0.7. Zero point 0.7 means it is more or less collaborated with the second cluster. So it will go and join with the second cluster. So like that, each and every pixel is grouped into different intensities. So that's fuzzy means. So it will show different intensities colors in different images. So this is the syntax. I don't have time. I think I should stop because I think it's your end of the day. I'll just run this picture. And the last line is that the membership matrix, and it is the image, smooth image is, so I this is the CNTR is the center of the cluster. So three clusters I have said. So each and every cluster will have one center. So three clusters will be there. U is the membership value. Final, because this FCM is done by iterations. First iteration, there will be one membership value. Second iteration, second membership value. And third, like that, it goes on. So here maximum iterations I have specified as 1,000. So it can take how many iterations it needs, how many iterations it needs to converge into one cluster it can take. So the final output should be three different clusters should be shown in the output. So it can take so many iterations to make that three different clusters. So this U is the final number of membership. So that is a segmented one. So that U is used to show the segmented output. And then we plot all the images. The first one is the smoothed image. The last loop is given to show all three clusters. So this is what I have given. So just I use this run button to run this code, and then it asks us to choose files because I have not given the file path here. So choose the files. So you have to store any image already, and just open that, and it shows me the output. So three different clusters of the brain. You can see this is the original image I took. This is a JPEG image I took. You can use DICOM images, but you have to download the very big size image. So you can see three different clusters. The first cluster shows the tumor and the skull. I said you this skull part should be removed because it has same intensity, same intensity values. So both has been shown. So you can have to remove this. You can also use other techniques like CNN or anything, and then check whether how it works or not. So this kind of works is also necessary nowadays. You can write a comparative papers between the fuzzy C means algorithm, um, like, and then the CNN algorithm. You can compare the outputs and write a paper based on that. And this is what I came to say you. Thank you for staying with me. I think I've stopped on my time. Thank you for staying with me. If any questions, you can ask me, please.
Participants, any questions to discuss? One participant has requested for the code you have explained just now, ma'am.
Okay, sure.
And
I can share you the code, but I don't know what is the media where I can share. I can give the presentation to the organizer to Chitra ma'am,
Yeah.
so that
Sure,
you
ma'am.
can communicate them.
Participants, yeah, after we got this presentation slides from the speakers, we'll share you. From that, you can get this code. And any other clarifications? I do not see any more questions in the chat, ma'am. And I thank you very much for the information session you have given us. And hope the participants will be benefited out of this. Thank you so much, ma'am.
Thank you so much for everyone to stay on the line. Thank you everyone. I appreciate everyone. Thank you.
Participants, I will post the feedback link now. Please do connected.
Recording stopped.
The feedback link is posted. I request all of you to fill the feedback form for today's session. And I want to remind you about the last day, that is tomorrow. Tomorrow we have our session starting at 2 p.m. So please do connect at 2 p.m. We have three sessions tomorrow. So I request all the participants to stay connected on the last day also. Thank you so much for attending today's session. We all will meet tomorrow. Thank you all.